Good afternoon, everybody. Thank you for joining us for the future of refrigerants. I have here, sorry, I just lost my voice. I have here Philip Johnston from Daikin Applied. He is the low GWP program leader for Daikin, and he will be taking us through the future of refrigerants. All mics are muted for this session. Feel free to ask any questions through the Q&A section. We will address all questions at the end of the session. And if you have any technical issues, feel free to put that into the chat. Please welcome Philip. Philip, take it away.
All right, can you hear me okay?
We can hear you.
Perfect. All right, well, welcome everybody. It's really my pleasure to be here, and hopefully you'll get a lot out of this. Yeah, my name is Philip Johnston. I have 20 years experience, all at Daikin Applied, formerly McQuay. And I did about 6 years of chemical, biochemical, environmental engineering before that. And that was all done in the province of Ontario, which is my home. I moved to the States about 20 years ago, 17 years ago to Minnesota. And I've been doing this low GWP refrigerant work for about 2.5 years now. So let's get started. Just to point out, I'm a member of the HRI Safe Refrigerant Transition Task Force. And when you see some HRI content, I'm allowed to use that. So those slides are specific. They use different color patterns versus some of the Daikin Applied slides. I encourage you to go there and check out their website. So some terms of use, move beyond that. This is what we're going to cover today. Some reasons for change, update on some legislation, standards, codes, both here in America and what I know about Canada. Then we're going to talk about potential replacement refrigerants for the commercial sector, but it also runs into the residential sector. So where are we today? Evolution of refrigerants, at least more recently, was all about the Montreal Protocol in the 90s. That was about protecting the ozone layer in the stratosphere to protect us from UV rays. So that eliminated the ozone depleting substances. And now we've moved on to climate change, also called greenhouse effect or global warming. The real key here is on the left-hand side. We need the greenhouse effect around the Earth. If we didn't have it, we'd be living on an icy rock. But we've induced more on the human side, both from the burning of fossil fuels creating CO2, but also from emissions of other pollutants such as refrigerants. And the big point here is the normal CO2 range over the last 400,000 years has been 200 to 300 ppm. But just in 2013, so not that long ago, we hit 400 ppm. And it's all tied to us through the Industrial Revolution. So we're moving on now to look at phasing down the use of HFCs and moving to other lower GWP HFCs, as well as a new type of refrigerant called HFOs, where it makes sense. And this is all through the Kigali Amendment to the Montreal Protocol. And that lines up with the Paris Agreement, which is a little bit different. The Paris Agreement is all encompassing, looking at every potential source of climate change. And anyone who signs on, any country that signs on to that has said they don't want to increase the surface temperature of the Earth by an additional 0.5 degree Celsius. And we've already increased the surface temperature of the Earth by 1 degree Celsius. And if you were to read some of the latest reports published, like the IPCC recent report, it looks like we could be hitting close to 3 degrees Celsius within some lifetimes of people here, maybe not mine. So why are we doing this? What do we have to do with it in the world of HVAC? Look on the left-hand side, you have total energy consumption over time through 2050, actually. And our industry, air conditioning in general, is forecasted to triple around the world. And that's due to economic growth. It's due to third world nations becoming more accustomed to the use of air conditioning and wanting air conditioning. So it's a good industry to be in. But with that, we have some duties that we need to take care of. On the right-hand side, just to show, they're expecting electricity consumption to go up by a factor of 6, CO2 emissions to double. So that's a good ratio. It means we're forecasting more renewable energy. But what does this really mean? It means we as an industry need to come up with super energy efficient air conditioning systems long term. And we probably need to move towards decarbonization of our electric grid. We need to electrify our buildings and move on to long-term more use of heat pumps around the world. And that's going to happen. It's already in play. So why are we really here, though? We're here to talk about HFCs and the Kigali Amendment. And the left-hand screen shows emissions in equivalency. So CO2 equivalent emissions, which is what the Kigali Amendment is all about. The models that were presented on the show in this blue band, where we could increase our HFC emissions by 6 to 9 times by 2100 if we don't put any controls in place. But if we put controls in place per the Kigali Amendment, you would follow that purple curve, which would basically mean our emissions would be pretty much flat to where like up and then down and pretty much insignificant. The real important thing is surface temperature. And if you look on the left hand or the right hand chart, temperature changes modeled under the do nothing scenario, where air conditioning is forecasted to triple. Just our industry globally, we could raise the surface temperature of the earth by 0.5 degree Celsius. And that would be the entire thing from the Paris Agreement, yet there are many other sources of greenhouse gas emissions. So we alone have that responsibility. If you put in the controls, though, the temperature change modeled due to HFC emissions would be about 0.06 degrees Celsius, so that purple line. So inconsequential, insignificant. And this is what industry is striving to do. And everyone wants it. Doesn't matter what the cause is. The governments are going there. Our citizens want us to do it. Who are our customers? And that's what we're looking at doing. So what is the Kigali Amendment to Montreal Protocol? Just focus on the red line. The red line is developed world. That's the United States and Canada. And we need to phase down our consumption in terms of CO2 equivalency down to 15% of the baseline. Now remember, the baseline's already in the past per the amendment, yet we're probably using more today than we were when the baseline was set. So we need to start driving that down. Now, this isn't just HVAC, it's every use of HFC emissions we need to get fit to 15%. And some of the data on the right-hand side, I won't spend a lot of time on, except to show that stationary air conditioning, which is HVAC, is probably the largest, if not the second largest, potential source of HFC emissions. So we have a big role to play. Let's look at some of the new next-gen refrigerants, and we'll review some of the current ones. Methane-based refrigerants, the 000 series, that's your R22. But guess what? It's also R32, which is not a new refrigerant. That makes up 50% of R410A down here, which is a 400 series, a zeotrope, meaning it has glide, so different boiling points of its refrigerant blends. You also have ethane-based series, 134A, being used in a lot of chillers today, or R123, also in chillers. And you have potentially new refrigerants, the 1000 series, unsaturated organic compounds. These are what the industry calls HFOs for olefin. O is olefin. If you're Canadian and you took chemistry, it was called an alkene. So it has a double carbon bond between there. And what's cool about that is that's a bit of a weaker bond when it comes to the atmosphere. So it breaks down fairly quickly. And then you tend to have coming forward, and I'm going to show you some 500 series also in the new lower GWP refrigerants. So they're blends that are blending primarily R32, but also 134A with some of these ultra low GWP HFOs. So there's some of that going on. Background ASHRAE 34 basics. Really, we've never used anything other than the A1 and a little bit of the B1. Even some of the future refrigerants can be A1, at least primarily for the replacement of chiller refrigerants. And they're really not no flammable. So you see I've crossed off this line. Everyone calls them non-flammable, but really it's no flame propagation at the ASHRAE 34 at the test conditions and during the tests. There is a new, relatively new classification of refrigerant, and that is that these A2L class refrigerants. So they are, some people call them mildly flammable, and these are going to become more common, being used, especially when I start showing you some options to replace R410A. So I'm going to give a real brief overview of standards. And this slide was created for the United States, but I'm going to talk about it in the context of how does it apply to Canada. ASHRAE Standard 34, it's all set up right now. It's under constant rev control. EPA SNAP program, if you ever hear about that, is how the EPA approves and bans specific refrigerants in specific sectors. And it's been updated to use R32 in residential and light commercial systems, but not yet for chillers. When it comes to the safety standards, the primary one is ASHRAE Standard 15, and it has been updated and under constant rev control to use some of these mildly flammable refrigerants. And also the UL standard, which is called 60335-2-40, third edition, is allows the use of mildly flammable refrigerants. And in fact, the fourth edition is out for public comment and public review right now. What's important about that? Well, first of all, the EPA has studied those standards, and in their Rule 23 to approve R32, they basically said these standards are ready and they allow the industry to launch refrigerants safely. Where we're kind of stumbling right now in America is you need to update your building codes. And we tend to have a couple of model building codes, and then they have to be adopted locally. And that's where they're at today. And in fact, by 2024, we need to get that done. And I'm going to show you a slide a little bit later to talk about where Canada's going. In the United States, very briefly, California tends to be the leader. And up until the end of last year, it was really California pushing a move. And they've already decided they're going to limit GWP in HVAC equipment to a 750 GWP. For PTACs and window air conditioners, January of 2023. For chillers, January of 24. For direct, like all other commercial and light commercial residential direct HVAC systems, other than VRF on January of 25, and then VRF gets one extra year by January of 26. The US itself, December 27th, 2020, President Trump signed the AIM Act into law. It was part of a large spending bill. That was a big surprise. No one expected that to happen. I will say this tells the EPA thou shalt phase down, shall manage HFC emissions, phasing down both the production and consumption of HFCs. They need to put in place reclamation procedures and reduce leaks. So they are focusing on that now, and they have yet to finalize their rules. It also allows the EPA to take what we call sector-based restrictions. And here's an example of one. Both Daikin, a number of other manufacturers, AHRI, our industry leader, several NGOs and states have all written petitions to the EPA saying, hey, line up with California. We're good to go with the 750 GWP on those dates. Please do it. So our assumption would be that chillers and DX systems will transition on January of 24 and 25. And of course, VRF January of 2026. There's a very high probability of that, but it's not set in stone just yet. So where's Canada at? Environment and Climate Change Canada has specifically looked at chillers, and they also want less than 750 GWP, and they're stating by January of 2025. They've also covered some other sectors like foams, aerosols, refrigeration, mobile air conditioning, cars, things like that. But there's been no regulations firmed up for the larger direct HVAC systems. And by larger, I mean the broader direct HVAC being residential, light commercial, and commercial. The B52 standard, which is the national code, has updated their CSA to match the UL standard, the third edition. So it permits the use of A2L refrigerants per that standard. I would say, though, that I'm told that the provinces adopt that standard or that code on their own, and that none have done it just yet. So just like the United States, where the local codes need to adopt it, it's time for Canada to do that. What do I think is going to happen, though? I actually think Canada will line up with the state's dates for everything, or slightly after. And we also want to point out that there's a demand in Canada for low GWP refrigerants. We see it in chillers today, and we see that pull. So here's an HRI slide. What's different? What's the same? Well, there's a lot when it comes to low GWP refrigerant movement. I think you have to say, you know, what's the big deal? What's all the fuss within the safety standards? I'm going to say the majority of the properties of Class A2L refrigerants are really no different than the A1 refrigerants. And that's primarily because when you think of R410A, it's 50% R32. And now we're just going to move to R32. The other 50% R125 was a flame retardant, and it impeded performance of that equipment, but it basically added a flame retardant to that blend. Now, what's different? Why is this an issue? Why do we have more flammable refrigerants to go to low GWP refrigerants? Well, it's basic chemistry. So there's a trade-off between flammability and basically stability in the atmosphere of refrigerants. As you remove fluorine atoms, there's a correlation. You remove fluorine atoms, they become less stable in the environment, so they break down more easily, good for the environment. But number two, they become more, as you add more hydrogen instead of fluorine atoms, they also tend to become more flammable. So that's why we're moving them. But I don't want you to panic about it. And what I also want you to know is you probably have, if you have newer appliances like a refrigerator or freezer, A3 refrigerants being used in extremely small quantities already in there today. So whether it's isobutane or propane. But looking down the bottom left, clearly you have no burning velocity for an A1 refrigerant at the test conditions, but here's heat of combustion on the vertical axis. And then here's an example of R32. It does have heat of combustion, but hey, so does 134A and R410A. So you can burn them. It's just they don't burn at the conditions. But let's compare heat of combustion for R32 to propane. Big difference. You know, it's at a factor of 5 or 6. So once you do burn it, very different heat of combustion. Burning velocity, that's a horizontal, how fast does the flame propagate? Well, R32 itself and some of the other proposed blends are all under 10 centimeters per second, which is the cutoff point for ASHRAE 34. Yet you look at something like propane, which is a fuel, you know, it's almost 46, 47 centimeters per second. So a huge difference, like a factor of about 10. So different there. Let's talk about ignition sources. Ignition sources are critical. And with A2Ls, you pretty much need an open flame to light them. Testing has been done in creation of the standards that show typical appliances and devices within a building environment will not have enough energy to light an A2L. And an example here would be minimum ignition energy for R32 is up over 10 but less than 100 in this rate. But if you look at something like propane, you know, it's down below 1, you know, 0.2, 0.3. So you're kind of talking about 100 times more energy is required just to ignite a typical A2L as compared to a common heating fuel. So they're not explosive and they're very difficult to ignite. Refrigerant concentration limits. Most commercial HVAC engineers and contractors are quite familiar with RCL. I'm not certain, I don't work in the residential side, but chances are they have some familiarity with that as well. The RCLs for common A2Ls are much lower than for R410A, and they're based on what they call the lower flammability limit, which is the minimum concentration of a refrigerant in air above which you can combust that gas, that mixture. So with A2Ls, you have RCLs that are in the 16,000 to 50,000 ppm range, whereas R410A was about 400 ppm. The RCL has a safety factor of 4 and versus the LFL, so it's well below. Why is this important? Well, all the safety standards basically do two things to prevent ignition. The idea is prevent ignition. How do they do that within the design of equipment and the systems? You need to have a leak, and the leak must exceed that lower flammability limit concentration. So with the use of RCLs and how we design the equipment and what we put in them and the system design, the idea is to keep the concentration that if there is a leak, it never exceeds the RCL. Number two, the ignition source cannot exceed the minimum ignition energy. So in the UL standards and in ASHRAE 15, we have to remove any piping away from potential ignition sources within our equipment. So for instance, contactors, things like that. So the safety standards deal with those in a whole bunch of ways, just deal with those two primary things to prevent ignition. So you might ask what's different about refrigerant sensing. Well, you definitely need sensors when you exceed a certain charge level within equipment. So in a window air conditioner where the refrigerant charges are extremely low, you won't need them. PTACs, you won't need them. Even certain small residential ground source heat pumps, water source heat pumps, you won't necessarily need those sensors because the concentration of refrigerants are so small. Just like the isobutane being used in a refrigerator or freezer, you don't have sensors in there. But once you hit a certain level, you're going to need sensors. Also, machinery rooms. So you think about chillers going into machinery rooms, you're going to need sensors there too. And that really isn't new. Certainly in machinery rooms, chillers can take up a lot of space with a lot of charge. So they would be doing that. For outdoor chillers, air-cooled chillers, even with an A2L refrigerant, you don't need sensors in the standard. And there are really no charge limits because they really don't fit the building code because they're outside. Now, manufacturers might provide them anyway, and certainly a contractor or someone engineering a system, if you were to put that air conditioner, that big, air-cooled chiller into a pit, you probably should think about doing that, much like you would do it in a machinery room. So just some examples of some things that have been added to the safety standards for a machinery room. You got safety ventilation control, interface inspection, refrigerant detectors. Again, really no different from detectors being used today, except the detectors they need to be able to detect the refrigerant you're using, and they're based more off RCL as the limit for that detector. They also need automatic self-testing, and then they're tested during installation and annually. Electrical protection, why? Again, to avoid minimum ignition energy, so they need to be separate. There can't be any flame-producing devices or hot surfaces above 1,209 degrees Fahrenheit. Different colored ports on the equipment, and then certain routine inspections are required. And above all, active mitigation for leaks. This isn't really new in a machinery room, but because A2Ls are a new class of refrigerants, they rewrote the standards. So some of the active mitigation, say volumes and set points, would be different. So let's talk about global warming potential. And I want you to know it's the direct global warming potential is from leaks. And that's whether it's in manufacturing of the equipment, system operation, or at end of life. The vast majority of that would happen in operation or at end of life. It has nothing to do with the efficiency of the equipment. And when you think about total equivalent warming impact over the life cycle of equipment, also called life cycle climate performance, the indirect effect from energy use in the United States is about 80 to 85% of the volume. So in parts of Canada where you have a lot of renewable electricity, this equation may be different. However, making a decision to go to a low GWP refrigerant that sacrifices efficiency of your system is going completely in the wrong direction. So we're trying to balance that, all right, when we make decisions around which refrigerants to use. Let's talk about some specific options out there for you. Is R123 is the refrigerant of choice by Trane in the past, and it cannot be used today in new equipment. Trane is offering another low pressure refrigerant called 514A. It's a blend. It has an HFO in it. It has, which comes with certain caveats or concerns, being a blend, but you are accustomed to blends with 410A, and this one has no glide. It has an ultra low GWP, very good of 2, and it's non-ASME, so Trane can use much of their R123 designs. Only Trane is offering it, so it may be expensive, and it's higher toxicity B1 or B, which is just like R123. So I suspect that if you as a user of this chiller are okay using R123, you're probably going to be okay using R514A. A lot of customers don't like using B1 refrigerants, so they probably won't like this as well. Now, the cool thing is Trane and many other manufacturers also have another option called R1233ZD. And the really great thing about this refrigerant, other than it being offered by almost every manufacturer, not Daikin applied just yet, but we're working on it, is that it meets a whole bunch of really great requirements. So it is a class A1 refrigerant. So that's a real winner. It's a single component refrigerant. That's a winner. Much easier to reclaim a single component refrigerant. Also has an ultra low GWP. And the cool thing is its efficiency is pretty darn good compared to R123, and its capacity is better. It does require ASME vessels. You get about a little more capacity than you do out of 123, and of course it's a toxicity category A, which is positive. I believe that this will become the long-term low pressure refrigerant to replace in a number of centrifugal chillers all around the world, and it's starting to look that way. It wins on a whole bunch of factors, from energy efficiency, total life cycle climate performance, no ozone issues, and has pretty darn good value, which is what I mean by on the economy side. So good potential there for everybody. When it comes to replacing 134A, which is the more common centrifugal and screw chiller refrigerant, there is something out there being used today called 513A. It is a blend. It's 44% R134A and has kind of a moderate GWP level of 572 in one of the ratings, 630 in the latest generation, but it's in that 600 range. Not bad, but you lose 3 to 5% efficiency by going to that blend. However, it serves its need. There are certain customers demanding this right now, and for a manufacturer like Daikin or JCI, Carrier, Trane, who all offer chillers today, they're able to do this with minor modifications to their new equipment. And I think some of the manufacturers are offering retrofit kits in certain parts of the world to update their equipment. So the real concern here is the efficiency and the fact that it's a blend. So there's another option that's been formulated, and one is you can look at it this way. There's 515B, which is a blend of the HFO R1234ZE. And why is that a blend? Well, 515B is a class A1, whereas 1234ZE is a class A2L. Now, this 515B is 91.1% 1234ZE and 8.9% of a different refrigerant that acts as a flame retardant. So the chemical producer blended just enough to squeeze into that A1 category to pass all the tests. And what's cool about 515B is it has a GWP of about 292, whereas the HFO in its pure form, the 1234ZE, has an ultra low GWP of about 1. This refrigerant is about the same efficiency as 134A, so it's pretty good. And we're starting to see this refrigerant being used in some of our equipment around the world, not just yet here in America, but we will be soon. And we're seeing it from other competitors as well for both screw and centrifugal chillers. When you compare the radar plots, where the larger coloring is favorable, you see that 1234ZE and 515B are pretty darn close in their value propositions, whether it's for ozone layer protection, life cycle climate performance, energy safety, and then ultimately value. But the real cool thing is, thing I want to point out is R134A is a really good performing refrigerant. The big knock against it is that GWP level, of over 1400. Because there's no double greens when it comes to efficiency or capacity. All the options are either slightly weaker on efficiency or on capacity. So to summarize, 513A has its place with a GWP of 631. It's a class A1. Its efficiency is a little bit worse, 3 to 5%, and its capacity is pretty similar. That's what I mean by yellow, similar to 134A. When it comes to the blend 515B, which again is a pretty decent GWP at 293, R123 at an ultra low GDP of 1. The efficiencies are pretty good, but their capacity is less. So we as a manufacturer need to provide improved compression in our chillers to make up for that capacity loss, but it is possible. So products here are on the way. I would say, I think if you're looking for an A1 refrigerant and don't need an ultra low GWP, 134A could be described as the best refrigerant today. I think long term we'll move towards the A2L 1234ZE or the blend 515B long term. Let's talk about replacements for R410A. R32 is undoubtedly proven and the most vastly used low GWP refrigerant, replacing R410A all around the world. And it started in 2012 in Japan, spread to Europe, other parts of Asia, Australia, and even into North America in 2016. You might be asking yourself, what do you mean North America 2016? Window air conditioners. So go check out in your home stores what's in window air conditioners. There's a very good chance it's got R32 on the data plate. So it's a single component refrigerant, widely used. It's used in over 100 countries, and there's more than 140 million units in operation today, manufactured by over 40 different companies. The residential market in Europe has hit about 40% R32 already, and it's going to be forecasted to be 85% of the residential market by 2023. What sort of products? Chillers, water source heat pump, VRF, mini splits, multi-splits, window ACs are all using it. And I think that when the Asian manufacturers of mini splits and multi-splits and VRF start importing those into the United States and Canada, they're going to keep using R32 over any other replacement refrigerants. And I'll show you why coming up. Just examples of some launches, all in Europe or Asia. Lennox has chillers, yes, it's true, in Europe, as well as rooftop units. And then Airedale, Daikin, Mitsubishi, and many others. And recently, Carrier also announced in April of 2020 that they were going to use R32 refrigerant in their commercial scroll chillers. Now, interestingly, they're going to use a refrigerant called R454B in their residential and light commercial chillers. So could be a split market or a split replacement where 410A is replaced by 2 or maybe 3 refrigerants here in North America. And certainly that's what they're seeing in Europe as well, is primarily R32 with a little bit of some other blends. So why R32? Why are there so many manufacturers using it globally? Well, R32 has been around a long time. It's 50% by mass of 410A. They're already manufacturing or producing 200,000 tons of it per year around the world. And so all they really have to do is double production, the producers, to get to low GWP refrigerants. Its cost, its availability are really a benefit because there are no patents around the molecule itself, and it's a simple molecule to produce. So you're going to have some of those cost or availability concerns with blends that are fairly proprietary, including those new man-made refrigerants called HFOs. So, but they have their place as well. So the new alternative blends that are being discussed to replace 410A are really 454B and R466A that are getting more attention, and they all use a refrigerant called R1234YF, which is an HFO, or CF3I, which is a fairly new refrigerant for HFC. They can't be widely manufactured around the world right now. So also being a single component, R32, means you're not going to lose composition if you have a leak. So over time, you can top it up within the equipment. You can charge it in liquid or gas phases, which is really cool. The ability to reclaim this refrigerant, which needs to become part of our lifestyle in this industry, is much easier anytime you have a single component refrigerant. And the reason we need to reclaim so much is because the Kigali Amendment will limit the production of HFCs and all refrigerants for that matter, probably going forward long term, like maybe a couple of decades from now. So we need to one, stop leaks. Number two, we got to reuse what's already been produced. Let's talk about performance. This chart was produced by NIST, so third-party reviewed researchers, and they studied thousands of refrigerants to look at, in this table, in a typical HVAC system, what could you replace 410A with? On the vertical axis, it shows efficiency normalized to 410A, more specifically COP. So 410A has a score of 1. Volumetric capacity, a score of 1. So 410A has got a score of 1. Of all the pure single component refrigerants out there, only one performs better than 410A, and that's in the top right-hand corner. That's R32. So there's nothing out there that exists today in terms of molecular chemistry that performs better than single component R32. So what comes next? You start looking at blends, and so here's an example of 454B, and one of the proposed blends is right in here, and it tends to lose a few percent of the capacity, but very similar performance to 410A. So what's cool is the chemical producers have come up with a refrigerant blend that has similar capacity and efficiency to 410A, but it doesn't improve upon the performance of our 410A. What did they do? They blended 68.9% R32 and 31.1% of this R123 that has about 5% less efficiency and 60% less capacity. Why so low on capacity? This was developed to replace 134A, but I've already told you, we're not going to use this in chillers because the efficiency isn't good enough, but it's being used in your cars today. So you'll see cars using 1234YF. So clearly when you blend down R32 with something else, you're going to sacrifice performance, and it tends to fall down in this area. So in summary on this, R32 really has incredible performance. We've seen increased capacity of about 10%, and we could leverage that by making our equipment much more energy efficient, or we could leverage it by cost reducing the equipment if we really wanted to hold efficiency. On the applied side, commercial, where I work, we're all about efficiency. So we took one of our Daikin Rebel inverter heat pump rooftop units, which are super energy efficient, and it uses scroll chillers. And we took R32 and dropped that into the R410A system. And we got up to 12% more energy efficiency using R32 than R410A in that unit in our lab. That's huge for the environment. It's huge for life cycle operating costs. Now, how did that happen? Well, if by dropping in the refrigerant you pick up capacity, you're selling a unit and they only need 10 tons. On an inverter unit, it's going to run slower. So our compressor amps were a heck of a lot less. The second thing is you needed a lot less refrigerant, so the pressure drop through the piping, through all the coils, was a lot less. So it was really cool. And alternatively, we used that same unit. We dropped in 454B, did charge determinations, and we lost some capacity. So we had to speed up, the inverter sped up the motor, and we ended up losing some efficiency, about 4% overall. So that's a really big deal. Are these typical? No, I don't think so. I think if you're going to look at fixed speed compression in residential systems, we as manufacturers are going to be able to design any of these refrigerants to hit any of your minimum energy codes. But albeit R32 is going to perform better if optimized. Hands down, it's the best performing refrigerant to replace 410A. That's really good for building owners, really great for the environment. So in summary then, R32, it's an A2L, has a 675 GWP, no glide, better on efficiency, capacity, and stability as compared to 410A. 454B that others will use has that composition that I mentioned, has an A2L, has an RCL almost identical to R32, but has that lower GWP value. And that's because they blended in this ultra low GWP HFO. But it has glide. You lose a little bit of efficiency, about the same efficiency as 410A, but you lose efficiency compared to R32, and you certainly lose a little bit of capacity compared to 410A. But it's a decent performing refrigerant. Then you see this other one that you may have heard about, R466A. 3-component blend, Look at that, still 49% R32, that's the base. They've blended in a very high global warming potential refrigerant as a flame retardant called R125. You want to get rid of that because it's really bad for the environment. And then they have this refrigerant called CF3I that no one's ever heard about before. Well, what is that? It's iodine. I stands for iodine. If you remember your chemistry in the periodic table, it's in the same column as fluorine, chlorine, bromine. And so it's a halogen. Not a lot of it around. CF3I is used today, I'm told, in jets. So away from humans as a fire extinguisher chemical, flame retardant, but it's not approved to be around humans. So it has some toxicity issues, but it's a rather expensive and will probably be a rather expensive component in this proprietary 3-component blend. Has an RCL quite similar, even though it's an A1, look at its RCL. It's less than 25% of 410A and in the same range as these other A2Ls. So why is that? Because of its toxicity. So just being an A1 on its own won't make this so widely used like 410A. I think you might still need refrigerant detection sensors, concentration or charge limits within certain spaces in a building might still become an issue. The real concern is back to that iodine, and that is the stability of the carbon iodine bond is a real concern. There's been a lot of publications and even a lot done by Train, who's been studying this, and they may use this refrigerant because they published a lot of data. And the concern is around the reliability of the equipment using this refrigerant. That carbon iodine bond, when it breaks down, it becomes an acid. And those acids will attack materials of construction of HVAC equipment. And that will happen at the standard accelerated life cycle tests that we perform. So the producer, Honeywell, has come up with some additives that they claim will deal with that issue, some chemical additives. We don't know what those additives are. We can't figure it out, and they're not telling us. But we've been told from Train that they do two things. One is they say it will prevent the breakdown of that bond, so stop the formation of acids or slow it down, but it still doesn't do it at the typical accelerated life cycle temperature at which manufacturers test. So it may happen within certain operating conditions. It may help it. The second additive that is in there is apparently a scavenger type additive that when acids do form, it binds with the acids so that very quickly so that it doesn't corrode the equipment. The question would be, how long does that last? I don't know. We don't know. So that's a concern for us. So I would say that R410A certainly has one really great benefit, and that's that it's a class A1, but it still has a very low RCL. And it certainly has 3 components with glide and has efficiency and capacity issues that per publications by Train are similar to 410A, but the data in their charts suggest it's a little bit worse. We also have the stability issues that are the biggest concern for me as a whole about this refrigerant. The other piece is, let's talk about GWPs themselves. I didn't say it earlier, and I probably should have. Global warming potential compares to CO2, and it's on a pound for pound, or in your mind, kilo versus kilo. So 1 kilo of R32 is the equivalent of 675 kilos of CO2 in terms of global warming. 454B has a 466 GWP on a kilo to kilo basis. But what's interesting is certain refrigerants perform better. They have better heat transfer capability. So some require less refrigerant and some require more to accomplish the same amount of cooling or heat pump heating. And the great thing about R32 is you need 20 to 40% less charge than 410A. So it kind of has an effective GWP of 475 in that range, under 500 for sure. Whereas 466A is a really heavy molecule and you need 10 to 20% more charge. So it has an effective GWP of around 800. So that's not very good either. So from our standpoint, I think what you're going to see in the market is potentially all three of these being used in North America. As of right now, no one is using 466A anywhere, and no competitors have announced they're going to use 466A. There's just been a lot of studies or information published. Competitors have definitely said they're going to use 32 and 454B, and R32 is just the one that's being used all around the world in very, very large numbers. So that's where that's going. If I was to summarize my deck as we move forward, the transition is underway. Our industry is ready and can safely commercialize low global warming potential refrigerants, and there are some very good performing refrigerants out there, and we can do it safely. There are certain steps that need to be taken, primarily around building codes, adoption of the new codes. So encourage your provinces to get on that. When it comes to low pressure centrifugal chillers, every manufacturer is offering the A1 R123 within chillers, and you can ask for that now. When it comes to R134A replacements, I think there will be R513A being used right now by some manufacturers. It's available, but I think long term, you'll see a migration to the ultra low GWP refrigerant R1234ZE or the blend R515B. When it comes to R410A replacements, there's nothing that performs as well as R32. It's very proven. It's easy to use and to reclaim. It's highly efficient, and that's how that works compared to 410A. And that ends my presentation. Thank you very much.
That's wonderful, Philip. Thank you so much. I encourage everyone to put your questions questions into the Q&A section. It's located at the bottom of your screen. Philip, we do have one that I'd like to read out. Maybe you can answer this. For rink arena facilities, what do you recommend to do to move away from R22 Freon in the next couple of years?
I know nothing about refrigeration, so I think it would be best for me as a professional engineer to defer that to have you go talk to your engineers for what that replacement ought to be.
Okay, I have another one here. Is it a drop in the 410A or any other like 404A?
Is what a drop in? R32? If that's what the question is.
Yep.
R32 is not, thank you, I got a yes. I should have made that clear. None of these refrigerants are truly drop-ins to 410A. Let's make that clear. The safety standards do not allow a class A2L or any other class of refrigerant to go into a different class of refrigerant in that system. So if the data plate says 410A, you got to stick with an A1 refrigerant. And so none of the A2Ls that are proposed and that are going to be used are true drop-ins. I would say as well, if you're picking up 10% capacity using R32, it's no drop-in. We have to do pretty serious redesigns of our equipment as a manufacturer to do that. So we need to make sure that our equipment is safe to use these refrigerants. And the other thing is with R466A, because of the stability concerns, if we were going to design around R466A, we would need to change because of the stability concerns, we'd have to have different materials within our equipment. It might even be not using brass, not using zinc, changing the polymers that are in certain things in the compressors. Is it possible? Yes, but there's a cost or an expense to that to move to that.
He also has
can
another
R32 be used?
Yeah, sorry, go on. Yeah.
Yeah, I pulled it up. I saw it now, how to do that. I'm not hearing R32 being used for walk-in coolers or freezers, but I'm not certain.
Okay, I have another question. Just give me one moment. It's can you please tell us more about the R32 in terms of toxicity?
I don't know what its occupational exposure limit is, so I'd refer you to its MSDS. So R30, you can Google that because there's so many manufacturers of it globally. The one manufacturer in the United States is called Arkema, ARKEMA. So go to their MSDS and see what it says. I will say that it's not the driving concern about R32 in that the room concentration limit is set by its lower flammability limit rather than its toxicity. So it would be, and its lower flammability limit, again, that is the minimum concentration of R32 in air at which you can get it to burn. So not too many issues with its toxicity as compared to what you're using today with 410A.
Okay, well, I think that ends the questions that we've received. Philip, do you want to leave us with any last thoughts? Oh, I have one more. I have one more. Somebody got it in under the time here.
Yeah.
Is there?
No, it's a good question. Make it.
Go ahead.
Yeah, if people aren't reading it, I should repeat it. Is there an A1 drop-in replacement for R410A for existing equipment? Is there something currently available? I am not aware of any drop-in replacements for R410A for existing equipment. I am also not aware of any development because I do not work inside the chemical research space. Daikin does make some of their own refrigerants, but that's a completely different business, and it's more the tail of the dog. You know, we're all about the equipment. I suspect that a manufacturer, a producer, will do research and come up with a very complicated blend that remains an A1 refrigerant that might give up on some capacity or efficiency for retrofit, but I don't know that it's going on. The examples of the refrigerants that are the ones that will be used, R32 and 454B, are all about new equipment, really. So
Okay.
I'm not aware of anything.
Okay. I have one more that came in through the chat. I'm just going to ask people to put it into the Q&A, but I'll ask it from the chat. What about ultra low temperature refrigerant replacement R508B?
It's not a business that I'm in. I'm in HVAC. I'd encourage HRAI to bring in someone from the refrigeration space, though, because we're getting some serious questions on it.
Okay.
Yeah.
Will do. That's a good point.
Why
Okay.
not?
Oh, sorry. Go on.
No, go ahead.
I was going to say, I wanted to say thank you to everybody for taking the time to attend this session, and I thank Philip as well for attending. Is there any way that people can get in touch with you or your team?
I guess you can find me on LinkedIn, Philip with one L, and Johnston, Johnston. It's probably got that mugshot that you saw early on the picture. So look me up there.
No problem. No problem. I wanted to say to everybody, this is recorded. We will be distributing it afterwards, and I'd really appreciate it if you can give us your feedback in our survey. It helps us develop some more presentations like this. Again, thank you so much, Philip, and I really appreciate your time.
You're welcome, and hope to see some of you soon north of the border.
No problem. No problem. Bye-bye.